Hello friends, welcome back to my YouTube channel. This is eighth part of my discussion on gas absorption, and today I will discuss one numerical example. I'm calling this as numerical example number 3 because it is the third numerical example in my discussion on gas absorption. And in this numerical example, we will learn how to find minimum liquid to gas ratio. Then by using the minimum liquid to gas ratio, how to get the operating liquid to gas ratio, and then how to find number of ideal stages in a tray column. So let us begin the discussion. To start with, we will look at the numerical statement. So light oil, which in this case is benzene. So light oil vapors contained in coal gas are to be removed by scrubbing the coal gas with a wash oil in a counter current absorption operation. The operation is to be carried out in a tray column. The gas enters the operation at a rate of 0.250 meter cube per second at 26 degrees Celsius and 1.07 into 10 to the power 5 Newton per meter square, and contains 2% by volume of light oil vapors. The entering wash oil contains 0.005 mole fraction of light oil and has an average molecular weight of 260. Calculate the wash oil rate if it is equal to 1.5 times the minimum rate. 95% removal of the solute is required in the operation. Also find the number of ideal stages required. At 26 degrees Celsius, the vapor pressure of benzene is 13330 Newton per meter square. So basically, there is a mixture of, in the coal gas, benzene vapors are present. They are calling benzene to be light oil. So these light oil vapors, or we can say that benzene vapors, they are present in a coal gas. And the objective is to remove those vapors, to remove the light oil vapors or to remove the benzene vapor from coal gas. And for that, what is done? The coal gas is scrubbed, washed with a liquid, which is a wash oil, the solvent in this case. And this is done in a counter current absorption operation. So the objective is here, counter current absorption operation is being used to absorb light oil or benzene vapors into a wash oil, which is the solvent in this case. Then this operation is to be carried out in a tray column. The counter current absorption operation, it is to be carried out in a tray column. The entering volumetric flow rate of the gas mixture, it is given to us. It is 0.250 meter cube per second. Temperature is given, it is 26 degrees Celsius. And pressure is also given, it is 1.07 into 10 to the power 5 Newton per meter square. Further, it is said that the entering gas mixture, it is containing 2% by volume of the light oil vapors. That is, the solute content of the inlet gas mixture, it is known to us. It is 2% by volume. Then the wash oil, which is used as a solvent, the wash oil is not pure. It is a recovered wash oil. That's why it is containing some amount of light oil, some amount of benzene in it. And what is that amount? It is 0.005 mole fraction. So in the entering wash oil, the benzene content or the light oil content is 0.005 mole fraction. And the wash oil, it has an average molecular weight of 260. So with this information, we are supposed to find out the rate at which wash oil is entering the column, the tray column, if it is to be 1.5 times the minimum rate. So in this case, the operating rate is 1.5 times the minimum rate. That means in this case, first of all, we will have to find the minimum rate and then multiply the minimum rate with 1.5, and you are going to get the operating wash oil rate. 95% removal of the solute is required in the operation. So 95% of whatever benzene vapors are present in the coal gas, they are to be removed, they are to be absorbed. Then we are also supposed to find the number of ideal stages that are required in the operation. They have given us the vapor pressure of benzene at 26 degrees Celsius. It is 13330 Newton per meter square. So with this information, let us solve the numerical. Let us move ahead. Okay, to begin with, let us list what is given to us. So in this case, the operation is benzene vapors, which we will be representing by capital E, are to be removed from their mixture with coal gas. And in this case, coal gas is the insoluble gas whose molar flow rate is denoted by GS. I have talked about this notations in my earlier videos. I am giving link to the entire playlist of my video lectures on gas absorption in the description section. And how this is to be done? This is to be done by absorbing benzene vapors into a wash oil. And then you can represent the operation schematically. So the gas mixture, it enters at the bottom of the tray column. Molar flow rate is Gn plus 1. So I have used this notations in my previous video lecture, which was on multistage counter current absorption. Link to the entire playlist is available in the description section. So the gas mixture is entering at a molar flow rate of Gn plus 1, and mole fraction of benzene vapors, that is solute in this case, is small yn plus 1. This is contacted with the wash oil, which enters the operation at a molar flow rate of L0, and it is containing x0 mole fraction of benzene in it, the solute. Then after the two phases come in contact with each other in the operation, liquid comes out at a molar flow rate of Ln, and it has a mole fraction of solute, that is benzene, xn in it. So after benzene vapors, they get absorbed into the liquid is coming out. Then the gas phase, it comes out at the top, or it is removed at the top. Its molar flow rate is G1, and some amount of benzene vapors, because 95% of benzene vapors are to be absorbed in the operation, so remaining 5% will come out with the outgoing gas, and small y1 will be mole fraction of those benzene vapors in the outgoing gas. Then for the inlet gas mixture, we have this information. The inlet gas mixture is coal gas whose molar flow rate is Gs, and plus benzene vapors, the solute, which we denote by capital E. The volumetric flow rate of the entering gas is given to us. Let us denote it as Vn plus 1. It is 0.250 meter cube per second. So it is different from Gn plus 1. Gn plus 1 is the molar flow rate, whereas Vn plus 1 is the volumetric flow rate. Then the entering gas mixture is containing 2% of E by volume. So we need to convert it to Yn plus 1, the mole fraction. So we will do that. Temperature, Of the entering gas mixture, it is given to us, it is 26 degrees Celsius. And if you convert it to Kelvin, it will be 273.15 plus 26. That is 299.15 Kelvin. Pressure is given to us. Pressure is 1.07 into 10 to the power 5 Newton per meter square. We need it in Newton per meter square, so we will keep it as it is. So this is the information that is available for the inlet gas mixture. Let us move ahead. Then for the inlet liquid is wash oil, which is the non-volatile liquid solvent in this case, whose molar flow rate we denote by LS, the notations that I have used. So wash oil plus benzene, that is the solute. Mole fraction of E in the inlet liquid, it is given to us. We denote that by X0. It is 0.005, X0 or X0. X0, let us say X0, that is 0.005. Then average molecular weight of the inlet liquid, it is given to us. Let us denote it as MW average, it is 260. Then the required rate of the inlet liquid is such that LS is equal to 1.5 into LS minimum. It is 1.5 times of LS minimum, the required rate. Then what is the requirement? The requirement is to remove 95% of E, 95% removal of E from the gas mixture, it is required. So whatever E enters, that is benzene vapors enter with this gas, 95% of those vapors are to be removed in the operation. So that is the outgoing gas will be containing 5% of E. So requirement is 95% removal of E from the gas mixture. Then vapor pressure of E, that is vapor pressure of pure benzene, it is given to us. Let us denote it as PA0. It is 13330 Newton per meter square. And what are we supposed to find? First, we have to get the required inlet liquid rate. That is, we have to get LS first and then get L0, the inlet liquid rate. And then we are also supposed to find out the number of ideal stages that are required to achieve this removal, to achieve 95% removal. So that is what is given to us. We have information about the inlet liquid, then we know what is the requirement, vapor pressure of A is given to us, and now we also know what are we supposed to find out. So I hope the given information is clear to you, and what to find, that is also clear to you. If you have any doubts, please mention them in the comment section. Let us know it. Now let us first understand the approach that we will be using in the approach that we will be using for solving this numerical example. So first we will find capital Yn plus 1, capital Y1 and capital X0. So small yn plus 1 first we will have to get from the inlet composition. For that we need to convert percentage volume to mole fraction, and then from once you get mole fraction, that is small yn plus 1, and then from small yn plus 1 you can get capital Yn plus 1. So capital Yn plus 1 we can get from small yn plus 1. Then capital Y1 we can get from capital Yn plus 1. For that we will use this information. 95% removal of E is required. That is given. That is the requirement. Capital X0 you can get from small x0. Small x0 is directly given to us. So from small x0 you can get capital X0. Then after that we have to get Gn plus 1 and then Gs, which are molar flow rates. We will be getting them in kilomole per second. So Gn plus 1 we will get from Vn plus 1, which is meter cube per second, And how are we going to get that? We will get that by using the ideal gas law. We will assume that the inlet gas mixture is an ideal gas mixture, and then we will apply the ideal gas law and then convert Vn plus 1, which is in meter cube per second, to Gn plus 1. Then Gs we will be getting from Gn plus 1 and small yn plus 1. Now both will be known to you. So by using those two quantities, we can get Gs. Then we will be getting the equilibrium relationship. And how are we going to get that? We are going to get that by applying Raoult's law. So for that, we need to assume that the liquid solution is an ideal liquid solution. So if that assumption is used, we can apply Raoult's law to describe the equilibrium between liquid and gas. So this is what we will be using. Once we get the equilibrium relationship, next we will find capital X and max. How? For that we will generate XY data. How are we going to generate the XY data? By using the equilibrium relationship that was obtained by using Raoult's law. Then we will be plotting the equilibrium curve. For that we will be plotting capital X on the x-axis, capital Y on the y-axis, and we will be getting the equilibrium curve. That is, we will be ready with the equilibrium diagram. Then after that, we will plot the operating line that corresponds to minimum liquid to gas ratio on the equilibrium diagram. So this is required for finding X in max. So that's why first we will be plotting the operating line that corresponds to the minimum liquid to gas ratio. And then from the slope of the operating line, you can get X and max. Then after that, we will be getting ELS minimum. So how are you going to get that? Once you have the operating line, let me first tell you, once we plot the operating line corresponding to the minimum liquid to gas ratio, one end of the operating line, the upper end of the operating line, the x coordinate of the upper end of the operating line will be X and max. So once X and max is known to us, we can go to the next step. What is that step? Finding ELS minimum. And for that, we will be using the equation of this operating line corresponding to the minimum liquid to gas ratio. Then once ELS minimum is known to us, we can find ELS, and then we can find EL0. ELS we can get from ELS minimum, because ELS is 1.5 times of ELS minimum that is given to us. And then from ELS and small x0, we can get capital EL0. And then once we have this values, you can find slope of the actual operating line, or I can say you can plot the actual operating line. And once the actual operating line is plotted, you can find the number of ideal stages, and that is the end of it. So we are going to report EL0 and ELS, and then finally we are going to report the number of ideal stages that will be required in a typical tray column. So that would be the approach for solving this numerical example. So I hope you have understood the steps that we will be following to solve this numerical example. If you have any doubts, you please mention them in the comment section. Let us move ahead. Okay, now let us start solving the numerical. First, we will find capital Yn plus 1. So for that, we have this information, percentage volume of E in the inlet gas mixture. It is given to us, it is 2. So we will assume the gas mixture to be ideal, and for ideal gas mixture, percentage volume is equal to percentage mole, that is 2. So therefore, mole fraction is mole percent divided by 100. So small Yn plus 1 is equal to 2 upon 100, which is 0.02. Then capital Yn plus 1 is given by this formula. Capital Yn plus 1 is equal to small yn plus 1 divided by 1 minus small yn plus 1. Therefore, capital Yn plus 1 is equal to 0.02 divided by 1 minus 0.02. That is, capital Yn plus 1 is equal to 0.02041. So, in this way, we get capital Yn plus 1. Now, capital Yn plus 1, which is 0.02041, it is defined as moles of E divided by moles of cool gas. So, moles of cool gas, they will remain, always remain in the gas mixture. It will not be changed. Now, the task is 95% of moles of E that are present in the inlet gas mixture that are to be removed. So, that's why we will use that information and then find capital Y1. We will use the information. What is the information? As per the requirement, 95% of the entering gas is to be removed. 95% of moles of E entering, which is 0.02041 per mole of coal gas. So 95% of the moles are to be removed. So that is, mathematically, this is capital Y1, that is the moles of E in the outgoing gas. E will be 5% of the moles that are entering, because the remaining 95% will be absorbed. So therefore, capital Y1 is 0.05 times of capital Yn plus 1. That is 5% of capital Yn plus 1. So therefore, capital Y1 is equal to 0.05 into 0.02041. That is, capital Y1 is equal to 0.00102. So in this way, we get capital Y1. Then we have to get capital X naught. Capital X naught is small x, or let us say we have to get capital X0. So capital X0 is small x0 upon 1 minus small x0. And small x0, it is given to us, it is 0.005. So therefore, capital X0 will be equal to 0.005 divided by 1 minus 0.005. That gives us capital X0 as 0.00503. So in this way, we get capital X0. So I hope you have understood how to get capital Yn plus 1, then how to get capital Y1, and then how to get capital X0. If you have any doubts, you please mention them in the comment section. So let us move ahead. Then next is we will be finding Gn plus 1, and for that we will assume ideal gas behavior. The gas phase is behaving ideally, and then therefore we can use the ideal gas law. So ideal gas law, when applied in this case, will be P into V n plus 1, that is equal to n plus 1 into R into T. So in this case, Vn plus 1, it is the volumetric flow rate which is given to us. It is 0.250 meter cube per second. So therefore, in this case, n plus 1 will be kilomole per second, which is nothing but Gn plus 1. So basically, we have to get n plus 1, and n plus 1 is nothing but Gn plus 1. So Vn plus 1 is given to us, it is 0.250 meter cube per second. P is given to us, total pressure, it is 1.07 into 10 to the power 5 Newton per meter square. Then R, the gas constant value, we will be using 8314. And if it is 8314, units will be meter cube Pascal per kilomole per Kelvin. That is, volume is in meter cube, pressure is in Pascal, which is Newton per meter square, amount of substance is in kilomole, and temperature is in Kelvin. So we will follow this units. Then temperature is 299.15 Kelvin, that is given to us. So in this case, as I said earlier, n plus 1 is nothing but Gn plus 1, which we are going to get. So therefore, if you use the given values, it will be 1.07 into 10 to the power 5 into 0.250, that is equal to Gn plus 1 into 8314 into 299.15. That is 1.07 into 10 to the power 5 into 0.250 divided by 8314 into 299.15, that is equal to Gn plus 1. And if you solve this, Gn plus 1 will be equal to 0.01076, and now it is kilomole per second. So in this way we get Gn plus 1. Now let us get Gs, and for that we will use this relation. Gs is Gn plus 1 into 1 minus small yn plus 1. Small yn plus 1 is 0.02 and Gn plus 1 we have just got. So therefore Gs will be equal to 0.01076 into 1 minus 0.02. That is Gs is equal to 0.01054 kilomole per second. So in this way we get Gs. So I hope now you know how to get Gn plus 1 in this case, in this particular numerical example, and then how to get Gs. If you have any doubt, you please mention that in the comment section. Let us move ahead. Then next we have to get the equilibrium relationship. And since we are considering the liquid solution to be ideal and the gas mixture to be ideal, so equilibrium between the gas mixture, ideal gas mixture and ideal liquid solution, it will be described by Raoult's law. And in this case the law will be partial pressure is equal to product of mole fraction in the liquid and vapor pressure. And partial pressure, according to Dalton's law, it is mole fraction in the gas phase, that is small y, into total pressure. So in this case y is mole fraction of A in the gas phase, P is the total pressure which is given to us, it is 1.07 into 10 to the power 5 Newton per meter square. Small x is mole fraction of A in the liquid phase, it is given to us, it is just mole fraction of A in the liquid phase in this equation. Then Pa naught, it is vapor pressure of E, and it is given to us, it is 13330 Newton per meter square. So and therefore the equation will be small y into 1.07 into 10 to the power 5, that is equal to small x into 13330. That is small y is equal to x into 13330 divided by 1.07 into 10 to the power 5. That is small y is equal to 0.125x. So this is the equilibrium relationship, but it is in terms of small y and small x. We need it in terms of capital X and capital Y. So next we will be converting this relationship in terms of capital X and capital Y. So for that we know that capital Y is small y upon 1 minus small y. So if I bring this term to this side and multiply the two terms, we will be having capital Y minus small y into capital Y is equal to small y. So then when I'll take this term to this side, so it will be capital Y is equal to small y plus small y into capital Y. In the next step I can take small y common. So therefore capital Y is equal to small y into 1 plus capital Y. That is small y will be equal to capital Y upon 1 plus capital Y. So that will give us relationship for small y, and small y will be capital Y divided by 1 plus capital Y. Similarly, we will have a relationship between small x and capital X. So small x will be capital X upon 1 plus capital X. So therefore, the equilibrium relationship in terms of capital Y and capital X will be of this form. Capital Y upon 1 plus capital Y is equal to 0.125 into capital X upon 1 plus capital X. Next we will be simplifying this relationship so as to get a simple relationship which will be easier for us to use. So let us move ahead. So we are getting the equilibrium relationship. We have got this equation, capital Y upon 1 plus capital Y is equal to 0.125 into capital X upon 1 plus capital X. So I will take reciprocal on both the sides. So it will be 1 plus capital Y divided by capital Y is equal to 1 plus capital X divided by 0.125 capital X. Then I will simplify it further. I will separate the denominator. So it will be 1 upon capital Y plus Y upon Y is 1. So 1 upon capital Y plus 1, that is equal to 1 plus capital X divided by 0.125 capital X. Then in the next step, I'll take this 1 to the other side. So it will be 1 upon capital Y is equal to 1 plus X divided by 0.125 into capital X minus 1. I will simplify this further. So that is 1 upon capital Y is equal to 1 plus capital X minus this into 1. So minus 0.125 capital X, the whole term divided by 0.125 capital X. So in the next step, you have 1 upon capital Y is equal to X minus 0.125 capital X is 0.875 capital X. So therefore 1 upon capital Y is equal to 1 plus 0.875 capital X divided by 0.125 capital X. Then I'll take reciprocal one more time. So that will give me capital Y is equal to 0.125 capital X divided by 1 plus 0.875 capital X. And that is a simple relationship between capital Y and capital X. So we will be using this relationship. So after we have got the equilibrium relationship in an appropriate form, next we will be getting X n max. So for that we need to plot the graph. And how are we going to plot the graph? For that we will generate XY data. And how are we going to generate that? We will assume different values of capital X, and by using the equilibrium relationship we will find corresponding values of capital Y. So in that way we will have the XY data. So assume different values of capital X, get the corresponding capital Y values from the equilibrium relationship. So then that will give us the data, XY data. Now what values of capital X are to be assumed? That will be based on the range. We know that X varies from X naught, which is 0.00503 to some higher value, whereas the range of capital Y is Y small y1, capital Y1 is 0.0503, whereas capital Yn plus 1 it is 0.0204. So based on this range, if I choose these values of capital X, I have shown the calculations. So if I choose capital X to be 0, 0.01, 0.03, 0.04, so I'm using an increment of 0.01. So what will be the increment in Y values? You can see over here. So it is 0.0012, 0.0025, and for capital X is equal to 0.1, a value of Y is 0.0115. But I need to go till Yn plus 1, which is 0.02041. So I will need more X values. So what I do, I decide I can use capital X values so that I will need less values of X. That will give less values of Y, and then I can easily plot the graph. So for that I will choose values of X in this way: 0, 0.04. I will skip the odd 0.01, 0.03. I will skip this. So I will choose 0, 0.02, 0.04, 0.06, 0.08, 0.1, then 0.12, so that it will be easy for me to cover the entire range of Y. So that is what I have done on. That is why I am done in. That is what I will be doing next. So let us do that. So as I said, we are getting Xn max, and now I have used these values of capital X. Capital X is 0.02, 0.04, 0.06. So I have used an increment of 0.02 in X, and therefore I get these values of capital Y. So with nearly 10 values, how many values of X? 3 plus 3, 6 plus 3, 9 plus 3. So with 12 different values of X, I get 12 different values of capital Y. And these are good for plotting the graph. So this is my XY data. I have generated it. I have generated it by using the equilibrium relationship. Now I will be plotting the graph. So let us do that. So capital X I will be plotting on the x-axis, capital Y I will be plotting on the y-axis, and I have chosen this scale. 1 centimeter on the x-axis is 0.05 and 1 centimeter on the y-axis is 0.005. So if I plot these values, I will be getting the equilibrium curve. So the equilibrium curve that I get, now it is in front of you. So this is the equilibrium curve that I will be obtaining. So now let us locate on the values that are known to us. Capital Yn plus 1 is known to us. It is 0.02401. So let us locate it. It comes over here. And therefore, after locating it, I will draw this horizontal line. Then I will locate capital Y1, which is 0.00102. So it will be located over here. Then x0 is known to me. It is 0.00503. So I will locate over here. So it will be located over here. And then you must have seen I have drawn this operating line. Now this operating line, what can you say about this operating line? This operating line, it touches the equilibrium curve at one point. So this operating line, it corresponds to the minimum liquid to gas ratio. And this end of the operating line, the upper end of the operating line, x coordinate of the upper end of the operating line, which will be xn max. So the upper end of the operating line, I get the x coordinate for this upper end, and that comes out to be 0.18, and that is nothing but xn max. So in this way, we have to get xn max. So what I have done, I have located yn plus 1, I have located y1, I have located x0, and then I have drawn from this starting point, I have drawn the operating line corresponding to minimum liquid to gas ratio. And what is that line? The line that touches the equilibrium curve in single point. Then after I draw the line, I get this point. Now my interest is to know the x coordinate of this point, because that is xn max, and you know the x coordinate comes out to be 0.18. So that's why xn max, it is 0.18. Now slope of this operating line is LS minimum divided by GS, that is equal to capital Yn plus 1 minus capital Y1 divided by xn max minus x0. So all terms on the right hand side are known to us, as GS is known to us, so we can easily get LS minimum. So we will be doing that in the next step. So I hope you have understood how we have got all this. If you have any doubts, you please mention that in the comment section. Let us move ahead. So next we will be getting LS minimum. So for that we will use the equation of the slope, which is LS minimum by GS is equal to capital Yn plus 1 minus capital Y1 divided by xn max minus x0. Yn plus 1, capital Yn plus 1 is 0.02041. Capital Y1 is 0.00102. Capital X0 is 0.00503. Capital Xn max is 0.18. And GS is 0.01054 kilomole per second. So let us use all these values. So therefore LS minimum divided by 0.01054, that is equal to 0.02041 minus 0.00102 divided by 0.18 minus 0.00503. So that is the LS minimum divided by 0.01054, and this difference is 0.01939 divided by this difference is 0.17497. That is LS minimum upon 0.01054, that is equal to, this ratio is 0.1108. That is LS minimum is equal to 0.1108 into 0.01054. That gives us LS minimum as 0.00117 kilomole per second. So in this way we get LS minimum. Now let us get LS. We know that LS is 1.5 times of LS minimum. So therefore LS is 1.5 into LS minimum is 0.00117. So that gives us LS as 0.00175 kilomole per second. Now we will get L0. So we know that LS is L0 into 1 minus small x0. So small x0 is 0.005 and LS we got, LS is 0.00175 we got, that is equal to L0 we have to get into 1 minus x0 is 0.005. So that gives us 0.00175 is equal to L0 into 0.995. That is 0.00175 divided by 0.995 is equal to L0. That gives us L0 as 0.00176 kilomole per second. So in this way we get L0, which is the inlet liquid rate. So first task, getting LS is completed, and from LS we have got L0. Next we have to find the number of ideal stages. So let us move ahead. Okay, so next is we will be plotting the actual operating line. So for that we have the graph that we plotted just now. We have the operating line corresponding to the minimum liquid to gas ratio. Now slope of the actual operating line will be LS upon GS divided is equal to capital YN plus 1 minus capital Y1 divided by capital XN minus capital X0. Now LS we obtained earlier, it is 0.00175 kilomole per second. GS we got earlier, it is 0.01054 kilomole per second. Capital YN plus 1 is 0.02041. Capital Y1 is 0.00102. So everything is known to us, and capital X0 is also 0.00503. So only XN is not known. So we can get XN, and then we will locate XN on this graph to get the upper end of the actual operating line. So if I use these values, it will be 0.00175 divided by 0.01054, that is equal to 0.02041 minus 0.00102 divided by XN minus 0.00503. Our objective is to get XN. So let us get that. So we have 0.00175 divided by 0.01054, that is equal to 0.02041 minus 0.00102 divided by capital XN minus 0.00503. So this ratio is 0.1662, that is equal to, this difference is 0.01939 divided by capital XN minus 0.00503, that is XN minus 0.00503, that is equal to 0.01939 divided by 0.1662, that is XN minus 0.00503. This ratio is that is equal to 0.1165. That is XN is equal to 0.1165 plus 0.00503. That gives us XN as 0.12168. So now once XN is known to us, that is X coordinate of the upper end of the actual operating line, now it is known to us. So we will use this to draw the actual operating line. So let us do that. So we have XN we got just now, it is 0.12168. So let us locate it. So XN will be located over here. Then I will draw a vertical line to get this point. Now the actual operating line will be starting at this point and it will be ending at this point, and therefore I will draw the actual operating line. Once actual operating line is drawn, next we have to draw the triangles that will represent equilibrium stages. Those triangles will be drawn between the actual operating line and the equilibrium curve. So we will start at this point. The construction will start at this point. We will move horizontally from this point to the equilibrium curve, then vertically from the equilibrium curve to the operating line, then horizontally from the operating line to the equilibrium curve, then vertically again to the operating line, horizontally to the equilibrium curve, vertically to the operating line, horizontally to the equilibrium curve, vertically to the operating line, horizontally to the equilibrium curve, vertically to the operating line, horizontally to the equilibrium curve, vertically to the operating line, horizontally to the equilibrium curve, vertically to the operating line. Now, once I reach this point and I try to draw the horizontal line, I am crossing this point. So I have reached the top tray. So I go horizontally and then I can draw vertically. If I go vertically, I have already crossed this point. So my construction is completed. Now I just have to count the number of triangles. So the initial triangles are very small. That's why I'm showing them. So this is first triangle. This is second triangle. This is third triangle. This is fourth triangle. This is fifth triangle. This is sixth one. This is seventh one. And this is something 7 point something. So I'm saying that it is 7.25. So since we have constructed approximately 7.25 triangles, the number of ideal stages in this case is 7.25. So the number of ideal stages, it is 7.25. So in this way, you have to construct the triangles between the operating line and actual operating line and the equilibrium curve, and then count those triangles. The number of triangles would be the number of ideal stages in this case. So for this numerical, the number of ideal stages come out to be 7.25. So if you try to complete the last stage, you will be, I'll just show, you'll be completing it like this, but you have already crossed this point. So whatever part of the stage comes till this point will be counted. So I have counted it to be 0.25. So that's why for this particular operation, in order to remove 95% of benzene vapors from the inlet coal gas, I would be requiring 7.25 number of ideal stages in a tray column. So with this, we get the answer to the final question. First we found out LS, then we found out L0, and now we have got the number of ideal stages. So with this, we complete the solution for this numerical example. With this, I will end my discussion for this video lecture. I hope you have understood the steps that I have followed in solving this numerical example. So thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. In my next video lecture, I will be discussing the concept of absorption factor. Till then, have a nice day. Bye bye, and hope to see you soon in my next video lecture.